Today's episode is sponsored by DL Chemical. They sell a range of polybutenes as well as ethylene propylene copolymers, which are called D-polybutene and D-cinol. Now, I'm actually more familiar with the D-cinol range, where I've used DS600 and DS1100 in a range of industrial gear oils. I've actually been really impressed by how well they incorporate into PAO fluids, especially considering how thick they are. But they've also got really high viscosity index, which can contribute a lot to your formulation. And overall, I've been really impressed with their oxidation stability in service as well. Considering how large the molecule is, they seem to be really shear stable. So if you're looking for an alternate to a very heavy PAO, give them a try. G'day everyone, welcome to Lubrication Experts. And today, we've got a really important topic because today we are discussing esters. And all things esters, we'll kind of delve into the basics and we'll start to get a little bit more advanced as we kind of travel along our journey today. I think this is a really important topic for a number of reasons. One, esters have always been parts of formulations, right? Synthetic esters, vegetable esters, we've used them since basically the dawn of lubricants. And maybe that's something that we'll get into as well. But I think with the focus on sustainability, bio-derived products, the capacity to have products that are biodegradable as well. Obviously, in Europe, there's the things like Eco Label and the Lusk List. Esters really form in many ways the kind of the core of all of that technology that sort of surrounds some of those, let's say, requirements or regulations. And so, an understanding of esters and what their place is in lubricating fluids, I think is kind of a really important, foundational bit of knowledge. And to be honest, when I look around at some of my customers, this is probably an area where it's a little bit lacking. So just before we jumped on the call, and I'll introduce Siegfried in a second, just before we jumped on the call, we were actually discussing how, let's say, for example, people who operate power plants are very familiar with mineral turbine oils, but let's say they've got an LM6000 on site as well. That's a synthetic polyol ester. Often their understanding of how to maintain that fluid is really shaped by their experience with mineral oils. And so because esters tend to be the exception rather than the rule, people generally have some misconceptions about them. So now, without further ado, I need to introduce our lubrication expert for this particular episode. So Mr. Siegfried Lucazeau, he's from Nyco, has a wealth of experience and is the marketing and projects manager over there. So really appreciate him. We obviously a bit of a time difference between Australia and Europe, but really appreciate him making time for us today to talk all things esters. So Siegfried, welcome.
Well, thank you very much for giving me the opportunity to do so.
Now, this is going to be a good one. So maybe let's start at the ground level, right? Which is frankly where I'm at, and where a lot of other people are too when it comes to esters.
Sure.
Maybe the first question would be, a lot of people have probably not dealt with esters since like high school chemistry in terms of formal definitions. So if you wouldn't mind defining what an ester is. And then the other thing which I think is helpful is to differentiate between what we might call natural esters and synthetic esters.
Sure, absolutely. So I think basically esters may be defined as a family of chemicals that all show the same chemical function. We call it the ester chemical function. And these chemicals normally result from the reaction between acids and alcohols. So that's a very simple definition, but this family is actually quite big and quite diverse in the variety of chemicals that we can find in it. But they all have in common that ester chemical function in them. So many esters actually occur naturally. We can find esters in nature, mainly as vegetable oils. But we can also find them in essential oils, for instance, and we can even find them in animals or even in our own body, right? So they're all over the place, basically. We do find them as vegetable oils mainly in nature, and chemically speaking, they would be triglycerides. Triglycerides of fatty acids with possibly the presence of unsaturated species. So that's what we're talking about when we say natural esters. We do mean vegetable oils or triglycerides for a more chemical name. Synthetic esters, however, are actually produced from raw materials, and they are actually designed. The very first step of the production of a synthetic ester is design. So we choose the chemical structure that we want to give to our compound, really, and then we run the chemical reaction between the selected acids and alcohols to get the very chemical structure that we want. And that's a very important feature of synthetic ester, that design flexibility, because it is the chemical structure that drives, at the end of the day, most of the performance features and the properties of these compounds. So having the right chemical structure means that we'll be able to have the right performance features for a given application. And that will also mean that we'll be able to raise the level of performance of these chemical compounds compared to natural esters.
Yeah. Okay. So that's interesting. So we're talking about obviously the difference between a natural product versus a synthetic product. I think
Yeah.
again, most people's understanding of this comes from the mineral oil world. So if the kind of the split there is, if it comes out of the ground as crude oil, then we refer to the product as it being a mineral oil. But basically, if we take raw materials and this is going to be a very technical term, we smash them together to make something new, then we get to call it a synthetic. And it seems like we're operating under the same principle, with synthetic esters. So
Yeah,
maybe I could
absolutely.
clear something up though, because sometimes we hear about synthetic esters being made from bio sources. So sometimes we hear about synthetic esters being made from something like palm oil or stearic acid and things like that. So can we make maybe a two-part question? Can we make synthetic esters from you know bio sources or fully renewable sources? And if that is the case, if you're making them from natural sources, what's that kind of distinction between made from natural sources but synthetic versus from natural sources and is simply a natural ester?
That's a very good question. So thank you, thank you for asking. So I think there's a general misconception about synthetic esters that would be products that only come from petroleum-derived raw materials and would not be biodegradable, but would be just high-performance products. And nothing could be further from the truth, actually, because synthetic esters simply means that you just take raw materials that you assemble together to get the chemical structure that you want. But these raw materials can actually be derived from petroleum or vegetable sources themselves. Okay, so synthetic does not mean it does not contain any biosource raw materials. It can actually contain raw materials coming from vegetables or petroleum or both. Okay, but the chemical structure will be the one that will, as much as it is possible, maximize the performance in the targeted lubricating applications. So the idea behind that is really to have the benefits of natural esters, like a high amount of renewable content, for instance, or even biodegradability, non-toxicity to the environment, but also improving the level of performance compared to a natural ester, which may have some drawbacks like, poor low temperature properties, for instance, or low resistance to oxidation, limited range of viscosities. So all of this might be, improved through the design of synthetic esters. But these synthetic esters can show a high amount of renewable content, anything between 0% to typically 85% of carbon of renewable origin. That's what you would typically find in a synthetic ester. And again, it's some synthetic esters, not all of them, because again, this will be structure dependent. Some of them will be biodegradable, non-toxic to the environment. it is possible to even make 100% biosourced synthetic esters. That's something that is technically possible.
Yeah, interesting. So, I mean, this is one of the like major sources of confusion when I talk to people who are using like EAL style products, right? Because
Yes.
for the uninitiated, all they see is ester, um, and that doesn't necessarily mean anything to a lot of people. And often I kind of have to explain. And I don't even know if this is right. You're sort of picking up if I'm explaining this incorrectly, but that it feels like in the EAL world, performance kind of bifurcates. So you have either natural vegetable based esters, or you have
Yeah.
synthetic based esters. And you know on one end you have extremely cheap, um, reasonably readily available, but like you said, only available in low viscosity grades. I think that's because for whatever reason, Mother Nature seems to like 16 to 18 carbon chains. Uh, I don't know
That's right.
why. There's probably a good reason for that. We'll ask a biologist.
Yes.
But you've got that
Mhm.
kind of low end performance. Like you said, you've got issues with oxidative and hydrolytic stability and all that. And then at the top end, you've got synthetic esters, which offer extremely good performance, but with a price that comes with it. And it almost feels like there's nothing in the middle, like there's no compromise. And so, a lot of people that I've worked with, certainly in the past, they tend to opt for the cheap version, thinking, well, it's all esters. How different can it possibly be? When of course, you peek under the hood a little bit, and it's they're both called esters, but that only really relates to the functional group, and you get wildly different performance. So that might lead into kind of the obvious question, which is, what is affecting ester performance? So you said we can make esters from a variety of components, whether they're natural, whether they're fossil derived, um, you know whether the end product is natural or synthetic. So how are we getting different properties from what are effectively the same kind of components, right? Like you said, we use acids and alcohols, we make an ester. So how come we can get such a wide variations in performance from what are on the face of it very similar building blocks?
Yeah, that's the beauty, I guess, of that technology, that design flexibility, really. So basically, I think the answer is really the choice of the raw materials that we can find that are available on the market. Um, and basically, we can obviously play with alcohols and acids. So um, the choice of the acid structure is key because it will actually determine a number of very important properties for lubricating applications. So the acid structure means the length of the acid chain, whether it's linear or branched. Is it highly branched? Is it only slightly branched, for instance? Is it saturated, non-saturated, slightly saturated, or unsaturated? So all of this, will play into it very greatly, I would say. And that will impact a number of properties like viscosity, resistance to oxidation, even cleanliness in operation will be impacted by the choice of acids. Friction modification also, the general rheology of the compound, and even the biodegradability will be impacted. Okay. So, for instance, longer acid chains will tend to increase viscosity. That makes sense. But it will also increase the flash points. It will tend to improve frictional benefits, just to mention but a few of the properties that will be impacted negatively or positively by the acid structure. Um, Oxidation stability, for instance, also will be slightly weaker using longer acid chains. Um, on the other hand, using branched acids will tend to increase viscosity pretty significantly, actually, for some acids, and it will improve oxidative stability. So that's another example of, the kind of range of properties that we can play with. So, the designing an ester has to do with choosing the right combination of short chains, longer chains, branch chains. You can use the three of them, for instance, in the same ester. So you do use a blend of acids in order to reach the right chemical structure with the right properties that you want to see in your product. Alcohols also play a role, obviously, but they will mainly impact the size of the molecule. There are exceptions to that general statement, but generally speaking, it will be true. So we're talking about the viscosity mainly. So if you want to increase the viscosity, you will probably use another alcohol with an increased number of hydroxyl groups on it. We need to mention, especially we at Nyco, that we can use some specific alcohols, and we call them neopolyols, that will show highly thermally and oxidatively stable or stability features, I would say. So this will generate very interesting esters for high temperature applications.
Okay, that's interesting. So, like any base oils that we're using for lubricants, as a general rule, the bigger it gets, the higher the viscosity is, right? You just have more interaction between the molecules, and that's kind of how viscosity emerges as a bulk phenomenon from these tiny molecules.
Yeah.
Does you obviously, one of the advantages of esters, well, in the synthetic case, right, is that you can get a pretty wide variety of iso grades that are available to you if you're working in the industrial world, right? So you can get some very high molecular weight synthetic esters. Um,
Yeah.
Does the role of the ester functional group kind of diminish as the molecule gets bigger? So in my very simple conception of it, right, is that maybe I'll have to flash it up on screen now what the ester functional group looks like, right? Because you've got because it's the reaction of an acid and an alcohol, you've got the carbonyl group, that double bond to an oxygen, and then you've got what looks like an alcohol group, the OH, coming off it. And then a lot of these esters might have one, two, three of these kind of ester functional groups reasonably close together, and then you've got the branches that sort of come out from it. It looks almost like a spider coming out from the body of the spider. But
Yeah.
in my simple conception of it, as you zoom out, the bigger the molecule gets, the ester functional group is taking up a much smaller proportion of the space in the molecule, and after a while,
Yes.
you have to get a very big molecule, but after a while, it just looks like any other kind of branched molecule with an ester functional group at the center. Does that make sense?
Yes. It certainly does. So I think it it really depends how you design and how you design the ester and how you produce it and the kind of chemical structure that you've got. So as you said, if you want to reach high viscosity levels, you will tend to use longer acid chains or branched acid chains, heavier structures. And then, as you said, the ester chemical function kind of gets lost in all of these carbon atoms around them, and that's precisely the notion of polarity that we can sometimes define with esters. That's basically the amount of oxygen compared to the amount of carbon in the molecule. Okay, so if you use heavy acids to produce your ester, then relatively the amount of ester chemical functions will be reduced compared to the amount of carbon in the rest of the molecule. And so we like to say that this reduces the polarity of the molecule, which means that you will have slightly less affinity for metal surfaces, but you will have improved affinity for the rest of the base oil if the ester is a component in the formulation, for instance, and that will tend, for instance, to improve frictional benefits. reducing polarity also has to do with lowering the impact on elastomers. Lowering the polarity also means that you may not compete with surface additives as much as you would do with a highly polar ester.
Yep.
So what you are saying, what you are describing is really the way that we can actually design an ester in order to reduce its polarity and improve elastomer compatibility, anti-wear response of the additives, for instance, and improve frictional benefits. Now, having said that, if you really want to reach ultra high viscosity levels, you will have to use another chemical structure. Because there's only so much you can do with simple neopolyesters, for instance, because you are limited in the size of the acid chains that you will be able to use. Okay, first, the bigger chains will not be available. That's one thing, and the second thing is that if you increase the acid chain length too much, you may have issues with low temperature properties.
Yep.
So there's a limit, as to what you can actually do to increase the viscosity. So the other way of increasing viscosity is to polymerize esters. We call them complex esters. So basically, we use standard ester species, and we will attach them together with diacids that will actually bridge those single units together. So by doing that, we will kind of polymerize the ester, and we will end up with much bigger structures with much higher viscosity levels. But in this case, the density of ester chemical functions will be a lot higher, if you understand what I mean.
Yep.
So in terms of polarity, that will be a much more difficult notion to explain in such a chemical structure, because you will have ester chemical functions, in the molecules, and you will have a certain density of those functions in the molecule. So polarity will be different there, and you will still have a ratio oxygen over carbon that could be pretty high. Actually, some of them might be so high that compatibility with hydrocarbons will not be very good. But at the same time, there will be very much film forming as a chemical compound with excellent frictional benefits, for instance.
Yeah, that's fantastic information. And if you don't mind, I wouldn't mind drilling down on this idea of polarity,
Yeah,
right? Because
absolutely.
that is kind of like the hallmark of the ester in many ways, right?
Right. Yeah.
So again, we're speaking to an audience of people that are ranging from field techs all the way through to formulation chemists. So we're trying to hit a pretty broad group of people here. But
Sure.
obviously,
Yes.
the advantage of esters in some ways is that it's polarity, in a few senses, right? So one, people would know that whenever we're making PAO synthetic lubricants, PAOs have a couple of issues. One, they tend to shrink seals. Two, they don't tend to dissolve additives very well. And so if you can mix an ester which is compatible with the PAO, then you can get some of that additive solubility and some of that seal swell. That's one reason. Another really good thing about esters is with that polarity, they can also dissolve a lot of those varnish byproducts, right? So
That's
when you
correct.
oxidize the base oil, you produce acids and ketones and those kinds of molecules, which tend to drop out of solution and form sludge and varnish. In the case of a full synthetic ester, they just tend to get absorbed by the base oil. Now, interestingly, when we talked at the very beginning about the discussion of the differences between mineral turbine oils and your fully synthetic turbine oils, which you'd see in the aviation sector. Now, the biggest difference between those from a deposition standpoint, if you like, is that the mineral turbine oils are all producing varnish and lacquer and sludge, and the aviation oil turbine oils all produce coke, which in again, and you correct me if I'm wrong, in my conception of it, it is that you're still producing the same oxidation products or similar species, but because of the polarity of the ester, they're able to be held in solution until such time as enough of those species kind of agglomerate together, so that the molecule becomes big enough that it actually falls out of solution. That's how I explained it anyway? Is that correct?
Yeah, I think you're right, Rafe, but I think this is only one part of the explanation.
Right.
For sure, using an ester brings polarity to the medium, and that helps with the solubility of additives and the solubility of oxidation products, definitely. Esters, thanks to their polarity, also will tend to contribute to some detergency effects on metal surfaces. That will definitely help keeping the metal surfaces clean. But they also show, at least some of them, okay, they also show some high levels of resistance to oxidation and thermal degradation, which means that it will take a longer time and it will take a higher temperature in order for the ester to degrade and break down into undesirable byproducts, side products that will eventually generate coke or varnishes or lacquers or particles or whatever you may think of in terms of oxidation
Yeah.
products. So they will do so. You're right. It's only a matter of time and temperature. It's organic chemistry. There is a temperature above which, or a time above which, any organic chemical will degrade. But with synthetic esters, again, provided they are carefully selected in terms of chemical structure, it will take a longer time and a longer temperature,
Yeah.
which means that they will generate less carbonaceous deposits and oxidation products. But you are absolutely correct in the fact that the being polar species, they contribute to detergency and dispersancy and solubility of all these oxidation products.
Yeah.
So that contributes to general cleanliness in operation.
Yeah, I've even seen, like, in some cases, I guess with some of the really high temperature chain oils, businesses using the degradation products and that sort of like very soft coke to their
Yes.
advantage, right? Like in very high temperature applications, that even when it breaks down, it almost forms like a solid lubricant, really, because it's such a kind of a soft carbon. Um, yeah, we got a little bit sidetracked there, but just to bring us back to the ester structures, I think it would be helpful because people see these terms thrown around, which I'm sure are very common in the ester world. But if you're not from the ester world, it can be a bit confusing to see, TMP esters, NPG esters, diesters, monoesters, and all this kind of stuff. So it might be worth kind of discussing what exactly all those are, um, and what are the kind of the pros and cons of each of these, and why do you see, for example, diesters are very common in compressor oils? Like, why would that be the case?
Right. So indeed, esters are a big family of products, and I think it's useful to you know uh, classify them into various categories, in particular for lubricating applications. So we've got monoesters to start with. So they are the reaction products from a monoalcohol on a monoacid. Okay. These are generally low viscosity products. So whenever you need low or even ultra low viscosity base fluids, monoesters are great products because they can really go very low. And they usually show very good frictional properties also. They are very linear
Mm.
structures, and as such, they will tend to um, assemble on a metal surface in a very structured way, and that gives a very interesting trouble film, and the resulting frictional properties are normally quite interesting. Then we've got diesters. As you mentioned, we hear a lot about diesters. So these products are esters of diacids. So I'm mentioning that because you may also think that you could produce a diester using a diol, with monoacids on them, but we would tend to call them diol esters rather than diesters. So really, diesters refer to esters of diacids.
And just to be clear for
These products,
anyone who's
yeah,
unfamiliar, right? That is something
sure,
that, like a molecule that contains two acid functional groups. So it might, for example,
that's
be
right.
a straight chain, and then it's got acids that are like facing outwards, and then you then have to react an alcohol to both sides of that to get you two ester functional groups along the chain. Yeah.
Absolutely, that's correct. We almost need a board to draw some
Yeah,
pictures.
yeah. I'll try and overlay some stuff here.
Right. So diesters would be considered as commodity products more than neopolyesters, for instance, and that's because they are used a lot as plasticizers in the polymer industry. So that means that they are products that are produced in large volumes, and they are pretty cheap as a result of that, at least cheaper than other esters, and they are available in large quantities. So that makes them interesting products, and that's why you can find them in compressor oils, for instance. At least a very specific class of diester would be phthalate esters in particular. Now, they're under scrutiny in terms of toxicity, so they may not be as popular as they used to be, but they have been used quite a lot as base fluids for ester-based compressor oils. That's correct. And then we've got a specific class of esters that I already mentioned before. They are called neopolyesters. So neopolyesters are esters of a very specific structure, alcohol structure. We call them neopolyols, right? We generally use four types of neopolyols to produce those esters: NPG, TMP, MPE, DPE. So these are the acronyms that you may hear of or find on the market very easily. So they actually stand for neopentoglycol. TMP stands for trimethylpropane. MPE for monopentaerythritol, and DPE dipentaerythritol. So all of these alcohol types are neopolyols. So when we esterify them with acids, you actually produce neopolyesters, and these products tend to show very, very good resistance to oxidation and thermal degradation, low volatility features generally also, and a high level of cleanliness in operations. So these are really the kind of chemical structures that you will find in high temperature applications in general. The first of which being aviation oils, of course, but we may also mention high temperature chain oils or even compressor oils. Amongst these four neopolyols, NPG, TMP, monopenta, dipenta, MPE, DPE, monopenta esters are probably the most temperature resistant. There's not a lot of difference between those four classes of esters, but if we had to pick one as the best in terms of temperature stability, monopenta would probably be the one. And then we've got complex esters. We touched about that a few minutes ago. So complex esters are basically neopolyesters that we would bridge with the help of a diacid to polymerize them, have bigger molecules, and higher viscosity levels. That's really the way to have access to high or even very high viscosity levels, up to, I don't know, at least 10,000 centistores, but you can find higher levels on the market using complex esters. They are very interesting structures because they kind of combine the properties of neopolyesters in terms of oxidation stability and cleanliness. Plus, they will also demonstrate excellent frictional benefits because as they are heavy structures with a lot of ester chemical functions in them, they will tend to absorb on metal surfaces very nicely. they will tend to show film forming properties, in other words, and that is excellent in terms of frictional benefits.
Yeah, cool. So, wow. So that's good because now I've got an explanation finally for what all those acronyms are.
Right.
After all these years, maybe to address kind of the elephant in the room would be to talk about some of the downsides of esters, some of which I think are overblown, some of which I think are legitimate. So, elastomer compatibility, for example, I've always thought is um, is maybe misunderstood in the sense that uh, any oil can be incompatible with elastomers because seals have their own complex chemistry, of their own. I haven't delved too deeply into seal chemistry, but it seems like they have their own base oils, their own additives, their own structures, which is just as, if not
Yes.
even more complex than the lubricant chemistry game. And realistically, what we're doing is we are trying to match, polarity between the base fluid in the seal and the base fluid in our lubricant, because a mismatch in the polarity of the two is going to either pull base oil into the seal or it's going to pull base oil out of the seal. Is my kind of conception of it. And so, if we have designed an elastomer system for mineral oils, then yeah, when it encounters the higher polarity of an ester, then that is going to potentially cause issues. Um,
Yes.
However, that's not the fault of the ester. That's the fault of kind of like the seal design. Anyway. That's how I've always kind of looked at it, and I think there's a bit of a maybe like a stink, if you want to call it that, that has lingered ever since the very very beginnings of the first synthetic engine oils when they put full 100% synthetic esters in, and people were blowing seals and all that kind of stuff. And it seems like people still remember that experience 60 years on, and it still has kind of like tarnished the name. So that one I'm not like as maybe as concerned about. Um, the one that always kind of comes up in particular is hydrolysis. Um, and the formation of acids. I'd like to touch on this one both because it's an interesting chemical reaction, but also from a condition monitoring standpoint. When people are trying to assess the health of their turbine oil or hydraulic oil or whatever it is over time, we have to track our metrics in a very different way than we do with mineral oils. So, would you mind just like talking a little bit about hydrolysis and what are some of the ways that ester chemistries can kind of reduce the effects of hydrolysis or prevent them?
Yeah, sure, absolutely. So, hydrolysis is basically the reverse reaction to esterification. So, if you put water in contact with an ester, theoretically at least, on the paper, the reaction will go backwards and will yield back acids and alcohols. So that's what hydrolysis is all about. So it's a chemical reality, I would say, but actually in operation it is rarely an issue. It is in some very specific conditions, but it's not very common, to be clear. So, in order to better understand the phenomenon, we have to remember that to carry out the esterification reaction, we do have to use high temperatures, normally exceeding 200 C, for a long time to take the reaction to completion. And so that basically means that if you want to do the same the other way, using water to break down the ester, you will need also a lot of time and high temperatures. Or if you do not use high temperatures, it will take an awfully long time. Sometimes so long that you won't see anything happening, before years sometimes. So we're really talking about conditions. That's what really makes sense. Um, So it's also useful to remind everybody that in order for hydrolysis to take place, you need water. That sounds obvious, but I still want to say it because if there's no water in the system, there's no hydrolysis whatsoever. Okay, so you need water and you need high amounts of water. So again, if there's only minor amounts of water getting into the system, there won't be much of an issue with hydrolysis. So conditions, temperature, the water, that has a lot to do with controlling hydrolysis. But the ester itself might be more or less resistant to hydrolysis, and that, just like the rest of the properties of esters, has to do with chemical structure. So we're talking about, and I'm sorry, that's a very chemical term, but we're talking about steric hindrance.
Mhm.
So that's really the way the molecule is built, and the way the chemical functions are actually accessible to water, because it needs to be in close contact with the molecule in order to make it react.
Yep.
So if we cannot reach the molecule because there is lots of carbon atoms and acid chains around it, then it will be a lot more difficult for water to degrade the molecule. So that's what we call steric
Yeah,
hindrance.
right.
And some
The
esters are a lot more resistant to hydrolysis than others.
Yeah, I was going to say on the steric hindrance issue, whenever I've had to explain it, you try and pull cultural terms, right? So, like if I'm in the US, I always try and explain it in terms of American football that you've got blockers that are that are trying to prevent the
Right,
water
yeah,
from getting to
exactly.
the and like we talked about, you've got the ester functional group is usually, well, not always, but often is at the core of the molecule, and so with
Yes.
those branched or semi-branched structures, if you can get enough stuff around around the ester functional group, then theoretically it's much more difficult for the water to get into contact and degrade it. So that would suggest also that the when you talk about polarity and the ratio between oxygen and carbon, that I guess the lower that ratio goes, theoretically, the more hydrolytically stable a molecule would be as well, right?
Um, yes, to some
Yeah.
extent, but I would also mention that the level of branching is probably more significant, more relevant to hydrolytic stability. So if you use branched acids rather than linear acids outside of their actual length, it will be a very powerful way of blocking the way of water to the ester chemical function.
Mhm. And
So branching, is very powerful in terms of steric hindrance.
yeah. Okay, that makes a lot of sense. And is there a standardized test? Because for people who are looking to select an ester, I mean, this is a minefield, right? There's so much complexity. It's not like selecting a PAO where you've got two options, right? There's conventional metallocene, pick your
You're
viscosity.
right.
Now we're talking about
Yeah.
hundreds of different variations on just
Yes.
a molecular functional group. So what are the kind of things that people should be looking for?
Right. There is a standard for measuring hydrolytic stability. It's the ASTM D2619. It's called the Coke bottle test. So you actually put your tested oil in a sealed bottle with an amount of water, and then you heat the whole system to 90 C for some time, and then you measure the acid number. So initially, this test was not designed for ester-based fluids, but it's still something that you can use to evaluate the resistance to hydrolysis of a finished lubrication. Now, I wouldn't like to use that as a way to select esters in particular. At least not that wouldn't be the only parameter to me, because hydrolytic stability is impacted by so many different parameters
Mm.
that I think that would sometimes be misleading. So, for instance, formulation also plays a very important role in hydrolytic stability. If you use additives that themselves are unstable in the presence of water, and they actually break down into acidic species, then you will increase hydrolytic instability very much. Acids actually tend to catalyze the esterification reaction as much as the hydrolysis reaction. So if you do generate acidic species in your formulation in the presence of water, then you will increase hydrolysis speed very much. So to be very concrete, we can think of phosphorus additives, for instance. Phosphorus additives will tend to be reactive with water, and they may break down into a phosphoric acid species, for instance. And phosphoric acid is a great catalyst for hydrolysis. So choosing additives that will show some level of stability in the presence of water is very important. But also we can mention the quality of the ester. Everything else being equal, if the quality of the ester is not good enough, it will impact hydrolytic stability. So when I say quality, it means purity, it means the acid number, it means the absence of metals, for instance, in the product. But it may also go through the right selection of raw materials. We have noticed at Nyco that some raw materials, would actually degrade hydrolytic stability compared to some others. They probably contain an impurity that is not detectable. It's absolutely not visible in the raw material itself or in the resulting ester, but still it impacts the hydrolytic stability. So there's a number of parameters that we can play with in order to put hydrolysis under control. But the simple measurement of hydrolytic stability of an ester base fluid is probably not enough as a piece of information to have a good feel of the hydrolytic stability of the finished formulation.
Yeah, interesting. Okay, so now we've got a picture for how we make an ester and different kinds of esters. So I think it'd be helpful to. We've already identified some of the major applications.
Yes.
Compressors, turbines. Now we've talked a little bit about EAL fluids also, um,
Yes.
as well as aviation turbine oils. Is there anywhere else that we've kind of missed in terms of applications?
I think probably the number one application would be refrigeration lubricants. Because you know that when the industry switched from CFCs to HFCs, again, I'm sorry, I'm talking about a little bit of chemistry
Yeah.
there, but so the refrigerant gases changed a number of years ago to protect the ozone layer, and now to to reduce the global warming potential of these chemicals. Um, the lubricants at the time stopped being compatible with the refrigerant gases, and the industry needed to have some much more polar lubricant oils to work in their refrigeration compressors, and this is when synthetic esters actually kicked in. And today, esters are still very much used in refrigeration lubricants. So that would probably be one of the biggest volumes worldwide for synthetic esters. Of course, we need to mention aviation lubricants. But as you mentioned, Rafe, some other high temperature lubricating applications. We've got compressor oils, that's correct. We've got high temperature chain oils, for instance. And there again, new polyesters will be used because, or thanks to their exceptional resistance to temperature, thermal degradation, and cleanliness. Fire safety also is something that might be mentioned. There is a lot of esters in metal working fluid applications. They are more like commodity esters. the level of quality of these esters may not be the same as for other applications because the requirements are not the same. But in terms of volumes worldwide, it's a lot, that's for sure. And then we can mention environmentally acceptable lubricants. So at this point in time, it's still a minor part of the market, but it's a growing segment, definitely. Esters may be biodegradable. So that's a very interesting feature for environmentally acceptable lubricants. So we can mention the European Eco Label. It's not a mandatory scheme; it's a label, really. So it's quite it's quite confidential, I would say, at this point in time. It's still a low volume, but the Vessel General Permit, now called the VIDA in the USA, which is a legal obligation, has really driven the use and production of these environmentally acceptable lubricants using esters for most of them. I think esters may be viewed also as components. You can certainly consider esters as being a full base fluid for the formulation of a lubricant, but they may also be used as a component or as an additive, for instance, in engine oils or transmission oils. They would be used as components, in particular for the frictional benefits that they would deliver. And we can also mention food grade applications in the food industry. Esters may be HX1 certified, which means that they are okay for use as a component of a lubricant that will be used in the food processing industry for incidental food contact. So there's quite a number of applications actually for esters.
Yeah, that's actually a pretty broad list once you sort of put them all together, right? Very, very interesting. So as we wrap up these interviews, I always like to ask a question kind of about the future. If you could gaze into your crystal ball, look forward 10 years into the future, what's the future of esters, and are there any cool technologies that Nyco's working on that you're able to talk about, or where do you see? Obviously, esters is a very broad category, as we've just discussed, but where do you see its place in the lubricants industry as we kind of go forward?
Right. I think, and that's my view of it, but I believe that the future of synthetic esters actually look bright because demand for higher performance lubricants is increasing, generally speaking. So that's a very general comment. Now, more specifically, I believe that performance in application will still be something of great value, delivered by esters, because performance in application means, amongst a few other things, extended lifetimes of lubricants. It also means energy efficiency through friction reduction. And energy efficiency means lower energy consumption, which means lower carbon emissions. So in a world where everybody focuses on carbon emissions and reducing carbon emissions and carbon neutrality on the long term, I think esters will be interesting technologies, if not key technologies, as far as lubrication is concerned, thanks to their level of performance and thanks to energy efficiency in particular. This does not mean that we won't work on their carbon footprints in a cradle-to-gate scope, but it means that really we want to make sure that these products, even if we try to reduce their carbon footprint, will remain performance products in application. I think we are also seeing a major change in the automotive industry. That's electrification. We hear a lot about it these days, of course. And I think synthetic esters do appear to be precious components for the new fluids that will be used in these electrified vehicles. So whether we consider battery cooling or whether we consider cooling the engine or lubricating the electrified transmission, esters will be precious components because they deliver fire safety, added fire safety, I would say, compared to traditional technologies. They deliver very good thermal properties, again, compared to traditional technologies, and they deliver frictional benefits. And these are key features for these applications. So this is certainly another area where we will spend time and promote Ester technology quite a lot.
Yeah, interesting. Well, Siegfried, thank you so much for coming to talk to us about all things esters. We'll have to get you back for a more, uh, esters 202 or whatever we want to call it. But no, really appreciate your time, and thanks for discussing.
Thank you very much, Ray, for giving me the opportunity to talk about esters. And I will be happy to give you more information in the future.
Sounds great. Sounds great.